This is Srikanth S, Assistant Professor of EEE Department. In this session, I am going to cover the operating principle of alternator and EMF equation. Alternator, the name itself says, which is going to generate alternating energy. An alternator is defined as a machine or generator which produces alternating current supply and converts mechanical energy into electrical energy. So it is also called as AC generator or synchronous generator, because this alternator is going to run at synchronous speed. Because of that reason, this is also called as synchronous generator. And in the alternator, in any machine, when we consider, we are going to have two windings. One is field winding and the rotor winding. That is, here, which is going to generate the main field. The winding which is going to generate the main field is called the field winding, and the winding which is placed on the rotor is called the rotor winding. So here the field winding, which is we are going to have the armature winding on the stator, because here the armature winding is of three-phase winding. So three windings we are going to have, whereas the rotor is going to have the field winding, which is going to have less value of winding. So we are placing the field winding on the rotor and armature winding on the stator, because in order to reduce the weight of the rotor. Here, when we reduce the weight of the rotor, the speed of the machine will increase, because we can easily rotate. Because when the weight of the rotor is more, then whatever the amount of mechanical energy required to turn the alternator, which will be more. So the mechanical energy which is required will be more. So in order to reduce the mechanical energy, we are placing the field winding on the rotor and armature winding on the stator. Let us see what are the advantages of keeping the field winding on the rotor and armature winding on the stator. Here, rotor winding is energized from the DC exciter, and alternate north and south poles are developed on the rotor. Rotor winding is energized with a external DC supply, and alternate north and south poles are developed on the rotor. When the rotor is rotated in the anti-clockwise direction by a prime mover, when the rotor is rotated by anti-clockwise direction by prime mover, the stator are armature conductors, because the rotor is developing the flux with north and south poles. So the stator or armature conductors are cut by the magnetic flux of rotor poles. The stator or armature conductors are going to cut by the magnetic flux, because rotor is rotating. So the rotor is having some amount of flux around it. So this flux is cutting by the stator conductors. So once there is a flux cutting action takes place, consequently EMF is induced in the armature conductors due to electromagnetic induction due to Faraday's laws of electromagnetic induction. What is Faraday's law? Whenever a conductor cuts the magnetic flux, an EMF will be induced. And the induced EMF is alternating since north and south poles of rotor alternatively pass the armature conductors. So the direction of induced EMF can be found by Fleming's right hand rule. The direction of induced EMF will be done with the Fleming's right hand rule, where forefinger indicates the flux and middle finger indicates the direction of armature current, and the thumb indicates the EMF, induced EMF direction. And the frequency is given as here. According to Faraday's law, the induced EMF is alternating since the north and south poles of rotor alternatively pass the armature conductors, because here the rotor is rotating. So every time whatever the flux which is changing, that is corresponding to during one period it will be in the half cycle, one will be north pole, and in the next half cycle it is under the south pole. So the direction of induced EMF can be found by Fleming's right hand rule, and the frequency is given by F is equals to Np by 60, where N is the speed of the rotor in RPM, whatever the mechanical speed we are going to give, and P is the number of poles. From this we can write the synchronous speed equation, which is equals to 120 F by P. This is the synchronous speed equation. And there are a lot of similarities between the alternator and DC generator, but there is one difference between them. Only the difference is both DC generator and alternator consists of armature and field winding. The difference is, in case of DC generator, armature winding is placed on the rotor and field winding is placed on the stator, where in this case the armature winding is placed on the stator part and field winding is placed on the rotor part, and it is connected to the DC supply. So here we are going to give two excitations. That's why synchronous machines or alternators are also called as doubly excited machine, because one is DC supply and another is the mechanical input. And here the advantages of having stationary armature. The first advantage is of high level of insulation. The alternator is usually designed for high level voltage operation. Generally, whatever the generating stations we are going to have, which is going to generate high voltage, so which require a good insulation to withstand the high voltage. As the stationary winding is free from the centrifugal forces, hence the insulation of winding becomes easier. So there won't be any mechanical forces on the stationary winding. So because of that, insulation of the winding becomes very easy. And the next advantage is that it reduces the armature reaction. Due to the stationary armature, more cross-sectional area is available. Hence, the maximum MMF will be passed from the armature slots, therefore, which reduces the leakage of the flux, that when the leakage of the flux is reduced, which will reduce the whatever the effects of the armature reaction. And whenever stator terminals are on the stator, when we place the armature winding, there is no need of brushes, because brushes are used to collect the current from the conductors. Here there is no need of brushes, only the terminals which we can take from the stator winding are enough. There is no need of brushes to collect the current from the alternator. And the next one is only two slip rings are required. Here, if the armature is of a three-phase alternator, which is not stationary revolving type, then it would require three slip rings for six-phase alternator, because it is going to have, for every winding we are going to have the two terminals. So for the two terminals we require one slip ring. So we will require the six slip rings. By making stationary, only two low voltage slip rings are required to excite the field winding by DC current. Here the slip rings are also reduced, so the machine cost is also reduces. And improved heat dissipation and ventilation. Due to low lamination and larger cross-sectional area on the stator core, the armature winding can be cooled and more efficiently as well as effectively. Here the dissipation of the heat, because when we place on the rotor, the area of the cross section is limited. When the area of the cross section is limited, the heat which is generating is going to affect the performance of the machine. Here, when the area of the cross section is more, the heat which is produced is going to be dissipated, so that the performance of the machine will be good. And now we will go with the rotating magnetic field. How we are going to get the rotating magnetic field in the generator. In alternators, a rotating magnetic field is a fundamental concept that plays a crucial role in generating alternating current. Alternators are devices that convert mechanical energy into electrical energy through electromagnetic induction. The concept of a rotating magnetic field was first introduced by Nikola Tesla. Here is how rotating magnetic field works in alternator. Stator windings. The alternators have a stationary part called the stator, which consists of coils or windings. And these windings are designed for generating three-phase supply, which is going to have three-phase windings in order to generate efficient electrical power. Now, the rotor with permanent magnets or electromagnets. The rotor is the rotating part of the alternator. It contains either permanent magnets or electromagnets. Number of poles on the rotor determines the frequency of the generated AC voltage. For a three-phase alternator, there are typically two or more sets of windings on the rotor. Now, generation of rotating magnetic field. When the rotor rotates, it induces the magnetic field that interacts with the stationary windings. If the rotor has permanent magnets, the magnetic field is fixed with the rotor. If the rotor has electromagnet, the magnetic field is created by supplying a direct current to this electromagnet. In the three-phase windings, which is going to generate three-phase flux. Because of that flux, the three-phase EMF is going to generate. So the rotation of magnetic field induces varying magnetic flux in the stator windings. So when the rotation of magnetic field is there, so which generates a varying magnetic flux in the stator windings, because once the rotor is rotating at different parts of the rotor is going to have different flux distribution. So because of that, which is going to produce a varying magnetic flux in the stator windings. According to Faraday's laws of electromagnetic induction, a change in magnetic flux in a coil which induces the EMF or voltage in the coil. Since the rotor's magnetic field is rotating, the induced voltage in the stator windings is alternating. And in many alternators, the stator windings are arranged in a three-phase configuration. As a result, three separate sets of windings produce three AC voltages with a 120 degrees phase difference. The combination of these three-phase voltages results in a three-phase alternating current. Here the rotating magnetic field is essential for efficient power generation in alternator. Here this rotating magnetic field is essential in order to generate efficient power, and it ensures the continuous and smooth production of alternating current, makes it suitable for various applications such as power generation in power plants and electrical distribution system and many other industrial applications. We need a smooth sine wave. In order to generate smooth sine wave, we need a perfect rotating magnetic field which will generate a perfect power with a smooth change in the voltage as sine wave. So that's why, because of this reason, these alternators and synchronous generators are used in the power plants or wherever we want to use in the electrical distribution system. We can use this synchronous generators. And efficiency and reliability. Here, rotating magnetic field offers high efficiency and reliability, leading to optimal performance and reduced maintenance requirements. And wide range of applications from electric vehicles to industrial machinery, the versatility of rotating magnetic field makes them essential in various sectors. And easy speed control. By adjusting the frequency and amplitude of the rotating magnetic fields, precise control of the speed is possible for these motors. And AC motors, the rotating magnetic field enables the operation of induction motors and synchronous motors, powering countless industrial applications. And transformers, by inducing voltage across the secondary windings, the transformers utilize rotating magnetic field to efficiently transfer the electrical energy. And magnetic resonance imaging. In MRI machine, powerful rotating magnetic fields create detailed images of internal body structures for medical diagnosis. These are the several applications of rotating magnetic field. Now we'll go with the different types of alternators. These alternators are classified into two types, that is based on the rotor construction, because stator construction is same for any machine. Only based on the rotor construction, the alternators are classified. These are, the first one is the salient pole rotor and the second one is the cylindrical pole rotor type. Now we'll go with the salient pole type. This is the salient pole type rotor, which is going to have the number of poles, that is even number of poles will be there. Here these poles are going to have alternate north and south poles. If this is the north pole and this will be the south pole. This is the north pole, another will be the south pole. Like this we are going to have n number of poles which are of even number. And in the salient pole rotor, on the salient pole rotor, we are going to place the winding such that which the winding has to produce alternate north and south poles. And this is the way we are going to place the rotor. And if this is considered, here the distance between the rotor and the stationary conductors is less, and here the rotor and stationary conductor is more. So there will be a difference in the flux distribution, that is called non-uniform flux distribution is going to be there in salient pole alternator. In order to reduce the non-uniform distribution of flux, we are going to have the poles with pole shoes. That is nothing but we are going to have the poles like this. This will reduce the some reduction in the non-uniform distribution of flux. And salient pole generators will have large diameter and short axial length, which is going to have a large diameter. Diameter of the salient pole machine is very high and short axial length. Axial length will be less. As the speed of the water turbine is slow, hence more number of poles are required to attain the frequency. Therefore, salient pole machines will have typically number of poles between 4 to 60 number of poles, and it is cheaper compared to cylindrical rotor machine for speeds below 1000 rpm. These are the generators which are cheaper as compared with the cylindrical rotor machine if the speed is less than 1000 rpm, which causes excessive windage losses. And flux distribution is not uniform due to the presence of salient poles. Hence, EMF waveform is generated is not good compared to cylindrical machine. And salient pole generators are employed in hydro power plants. And this is the cylindrical or non-salient type rotor. Here we are going to have, throughout the rotor, we are going to have the conductors which are going to place different slots will be there to place the field winding. So on these places we are going to place the field windings, and which also produce alternate north and south poles. Here it is like a circular shape, complete circular shape. So the flux distribution in this motor is uniform. So when the flux distribution is uniform in the alternator, so the EMF generated in the alternator is also uniform, and there is no mechanical disturbances because of the non-uniform flux distribution. A non-salient pole generator will have smaller diameter and longer axial length. They are used for high speed operations. Typically speed will be 1500 to 3000 rpm, where we are using in the thermal power plants. And it is better in dynamic balancing because of absence of salient poles, because the mechanical imbalance will be there, because when there is a non-uniform distribution, that will be balanced in the cylindrical rotor. And here we are going to have less windage losses. Here the air gap is very less. When the air gap is less, we are going to have less windage loss, and which is going to have robust construction and noiseless operation, and nearly sinusoidal flux distribution around the periphery, therefore, which gives a better EMF waveform than salient pole machine. So here we are going to get a good output waveform than the salient pole machine. And these are the some of the applications of alternators: automobiles, electrical power generation plants, marine applications, diesel electrical multiple units, radio frequency transmission. And the advantages of an alternator are: it is cheap, low weight, low maintenance, construction is simple, and it is robust and more compact. As compared with the DC generator, here there is no commutator. So when there is no commutator, the maintenance is easy. Now let us go with the EMF equation of an alternator. An EMF induced by an alternator depends on the flux which is induced by the n number of conductors. So let us consider first Z as number of conductors in series per phase. For each phase, how many number of conductors are connected in the stator winding? That is nothing but Z. And where Z is equals to 2T, where T is the number of coils or turns per phase. One turn has two coil sets or conductor as shown in the below diagram. That is here, which is shown clearly. One turn or coil is going to have two coil sides, that is one conductor. This is one conductor and this is another conductor. And P is the number of poles, F is frequency in hertz, phi is the flux per pole, Kp is the pitch factor, and Kd is the distribution factor, and Kf is the form factor, where N is the speed of the rotor in RPM, that is revolutions per minute. And if we take for one revolution, this N by 60 is nothing but speed of the rotor in revolutions per second. N is the speed of the rotor in revolutions per minute. N by 60 is the speed of the rotor in revolutions per second. Time taken by the rotor to complete one revolution is equals to dt is equals to 1 by n by 60, 1 by n by 60, which is equals to 60 by n seconds. 60 by n seconds. In one revolution of the rotor, the total flux cut by each conductor in the stator poles, which is in one complete revolution, flux is the flux which is phi is the flux which is going to cut by the each conductor, and P is the number of poles which are going to there. In one revolution, P number of poles are going to be cut. So d phi is equals to phi into P. By Faraday's laws of electromagnetic induction, EMF induced is proportional to rate of change of flux. So here average EMF induced per conductor is equals to d phi by dt. Here d phi we have calculated phi into P divided by dt is equals to 60 by N, which is equals to phi Np by 60. And we know the frequency of induced EMF F is equals to Pn by 120, where N is equals to 120 F by P. So here in place of N, if we substitute 120 F by P, that will give us average induced EMF per conductor is equals to 2 phi F. Here Z are the number of conductors in series per phase. So the average EMF induced per conductor is equals to 2 phi Fz. So the RMS value of EMF per phase is equals to form factor into average value of induced EMF. That is equals to 1.11 into 4 phi Ft. So the RMS value of EMF per phase is equals to 4.44 phi Ft volts. This is the EMF induced. But because of the different windings which is having full pitched and concentrated coil winding, there are different factors we are going to have, that is pitch factor, distribution factor and form factor. So the actual induced EMF per phase is equals to 4.44 into Kp Kd phi Ft. This is if we write only in terms of pitch factor and distribution factor. If we want to write in terms of form factor also, that is equals to 4 into Kf Kp Kd phi Ft volts. This is the EMF which is generated in the alternator. Now let us go with the examples. A 3-phase 16-pole alternator has a star connected winding with 144 slots and 10 conductors per slot. The flux per pole is 0.02 Webers and which is sinusoidally distributed, and the speed is 375 RPM. Find the frequency of the induced EMF, phase EMF and line EMF. Assume the coil as full pitched. Here the given data is number of poles as 16, slots is equals to 144 and Z is equals to 10 conductors per slot. Phi is equals to 0.02 Webers and N is 375 RPM. For full pitch coil, Kp is equals to 1. We need to calculate the frequency, E phase and E line. So in order to calculate, first let us calculate what is the distribution factor. So first frequency is equals to Pn by 120, that is 16 into 375 by 120, where the frequency we are going to get it as 50 Hz. The EMF equation of an alternator is given by 4.44 Kp Kd phi Ft. In this, Kp value is for full pitch, Kp value is 1 and distribution factor we need to calculate, where Kd is equals to sin m beta by 2 by m sin beta by 2. Here m is the number of slots per pole per phase, which is equals to number of slots per pole per phase. Number of slots are given as 144 divided by number of poles are 16 divided by phases are 3. So which will get M value as 3, and where N is equals to number of slots per pole, that is equals to 144 by 16, that is 9. And here beta is equals to 180 degrees by N, that is equals to 180 by 9, which is 20 degrees. Where KD is equals to sine 3 into 20 by 2 by 3 sine 20 by 2, which is equals to sine 30 by 3 sine 10, which is equals to 0.96. Where Z is equals to 10 conductors per slot per phase, which is equals to 10 into 144 by 3, which is equals to 480 volts. Where T is equals to Z by 2, that is 480 by 2, which is 240 volts, 240 conductors. Where E phase is equals to 4.44 into Kp value is 1, Kd value we got it as 0.96 into 0.02 into 50 into 240. 0.02 is the flux, which is equals to 1022.97 volts. This is the E phase. And line voltage will be always root 3 times the E phase, which is equals to root 3 into 1022, where we are going to get it as 1771.83 volts. Now we'll go with the another problem. A 3-phase 50 Hz alternator is running at 600 rpm and has a 2-layer winding, 12 turns per coil, 4 slots per pole per phase, and coil pitch of 10 slots. Let us find the EMF induced per phase if the flux per pole is 0.035 Webers. So in order to calculate the EMF induced per phase, first we need to calculate what is the KD value. Here the number of poles is equals to 120 F by N. Here the number of poles we got it as 4. And number of slots is equals to 4 into 3 into 10. 4 slots per pole per phase. 4 into 3 into 10. For coil pitch, each coil pitch is having 10 slots. That is equals to 120. So alpha is equals to 180 by 10 divided by 180 into 10 by 120, which is 15 degrees. Where KD is equals to sine 4 is the M value. Slots per pole per phase is given as 4. Sine 4 into 15 by 2 divided by 4 into sine 15 by 2, which we are going to get it as 0.958. This is the KD value. The pole pitch is of 120 by 10, which is equals to 12 slots. So beta is equals to 12 minus 10 into 15, which is equals to 30 degrees. So here, when the beta value is 30, pitch factor Kp is equals to cos 30 by 2, which is equals to 0.966. So the EMF equation of alternator ERMS is equals to 4.44 phi ft into Kp Kd, which is equals to 4.44 into 0.035 into 50 into 480 is the number of turns into 0.958 into 0.966. This is the Kp value. This is the Kp value and this is the Kd value, where ERMS value is equals to 3451 volts. In this session, we have discussed the working principle of alternator and EMF equation of alternator along with the problems on EMF equation. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.